Okay, today we are going to fill in some of the missing information in the notebook. Keep in mind, if you are pacing yourself on your vocabulary assignment, you should have one page front and back completed at this point. And today's assignment, if you want to call it that, would be to do the front page or the front part of the second page. Just FYI, I'm considering counting that as two homework assignments, maybe even four homework assignments. I haven't really figured it out yet, but maybe like the entire front and back of the first page would be one assignment. The entire front and back of the second page would be a second assignment. This 6 weeks, we're not going to have a lot of opportunity for many grades with all of the testing stuff that's going to be going on. So we're going to have to kind of pick up grades where we can find them. Okay, so stay on top of your vocabulary. That packet will be due on Monday. Okay, so we're going to start off in reporting category 1. Okay, in reporting category 1 on the left-hand page, we have talked about the differences between Euclidean and non-Euclidean geometry. Okay, Euclidean and non-Euclidean, and we filled in these guys as we went in. So let me just kind of basically run down that real quick. Under the non-Euclidean geometry, there's three different kinds. There was the spherical, there was the hyperbolic, and there's the taxicab geometry. Okay, so you've got these two basic subdivisions, Euclidean and non-Euclidean, and there are three different types of non-Euclidean geometry, spherical, hyperbolic, and taxicab, and you should already have those labeled. We talked about what it means to be parallel in Euclidean geometry, and then we also talked about what it meant to be perpendicular. And if you open up your Euclidean flap, you should have a diagram like that. And we compared that to what it means to be parallel and perpendicular in these other geometries. Taxicab is not all that different from Euclidean geometry. The only difference was in taxicab geometry, you're not allowed to violate the space off of the grid. Okay, so you can't cross into the open space. Spherical and hyperbolic geometry did a few things to what our idea of what we think of as parallel. Spherical geometry caused our lines to bend in toward each other. Okay, that's not typically what we think of as parallel, but there is a location, okay, that is there where they are exactly parallel by Euclid's definition. They just don't stay that way because of the nature of the curved surface. Same thing with hyperbolic. Again, it doesn't look like our typical definition of parallel, but there is one location where, yes, they are in fact parallel, but again, they just don't stay that way because of the nature of the curved surface. So you should have those four diagrams in your in that first little foldable on the different types of geometries. The other one was basically the idea of what we've come to think of as polygons. Okay, so we did triangles. Okay, any 3 points in Euclidean geometry, line segments connect them. Same thing with spherical and hyperbolic geometries. But again, due to the nature of the curvature of the surfaces, spherical geometry is actually going to cause these line segments that are trying to connect the vertices to appear bowed outward as they move along the curved surface. So it's kind of like a fat triangle. And with hyperbolic geometry, same basic idea, but in this time they're kind of caved inwards, okay, because of the curvature of the surface. So you get a skinny triangle. And then taxicab geometry is kind of the goofball. You've got 3 points, you want to connect them, but you have to stay on the grid lines. So that can cause you to have to vary, kind of the directions or whatever that you're traveling in order to get from one point to the other. But as long as you are moving from one point to the other with the intention of getting directly from one point to the other, any direction that you go is acceptable in taxicab geometry. So in those first four flaps there, you've got definitions of parallel and perpendicular for the four different types of geometry. You've got definitions for polygons for your four different types of geometries. Okay, the next thing you've got there down at the bottom is we have flaps that are specifically on inductive reasoning and deductive reasoning. Okay, we talked about this briefly as we were putting it into the folder. What is inductive reasoning? We're going to write basically a definition underneath the flap for inductive reasoning. What is it? Anybody remember? Okay. Inductive reasoning is basically predictions or statements that are based upon observable patterns. Okay, observable patterns. So these are predictions or statements, if you'd rather write that are based on observable patterns. Okay, so we'll write that underneath the flap for inductive reasoning. And if you remember, the example that I'm prone to using is the dog. Okay, where you see a dog, you reach down to pet it, it bites you, and then tomorrow you do the same thing again, it bites you again. The next day you reach down to pet it, it bites you again. So what's going to happen the fourth day? If you see the dog, you reach down to pet it, well, the obvious prediction would be that the dog is going to bite you, but do you know for a fact that's going to happen? No, you don't. It's just the best statement that we can make, the best prediction that we can make based upon the observation that it is happening on a daily basis. That is inductive reasoning. Okay. We also talked about what deductive reasoning means. Okay, everybody remember what deductive reasoning is now? Yeah, that's exactly it. Okay. Still predictions or statements, just like with inductive reasoning, only deductive reasoning is based upon factual information. Okay, so it's still predictions based on, but this time it's factual information. Okay, so that'll go underneath your flap for deductive reasoning. And this one's a little bit more of a reach, to try to come up with an example on it. It's just kind of like saying, you're sitting here in class. That's a fact. We're taking notes on geometry. That's a fact. So deductive reasoning statements would be something along the lines of, you must be a student that is enrolled at Odessa High School. That's a fact. Otherwise, you wouldn't be sitting here in this classroom right now taking these geometry notes. Or I could say you are a teenager, because you wouldn't be here sitting here taking geometry notes unless you were a teenager. You got up and came to school this morning. That's deductive reasoning. Otherwise, you wouldn't be sitting here right now taking these notes. Those are all deductive reasoning statements. Okay, so there's information. So if you get confused over what inductive or deductive reasoning is, now you can pull that flap up and you got a definition directly underneath it. Um, that's all of the written information that we're going to put into reporting category 1 at this time. The rest of it deals with practice cards. So turn the page, get into reporting category 2. The information we're going to put on reporting category 2 is down at the bottom of the right-hand page. We're going to be dealing with the 3 triangles that we've got down at the bottom. Okay. The foldable on the left-hand side down there looks like this guy. Okay. We're going to put some information to go along with this. Now, when we put this in here, I asked you specifically, you've got a right triangle that's got a 4 and a 5 on the sides of it, okay? And I asked you if you knew off the top of your head what the third side of the triangle was going to be, and y'all told me it would be 3. It's going to be a 3, and that's absolutely right. So if you want to, go ahead and take your pencil there, or a different color or something like that. Write in the 3. How do we know that that was going to be a 3? Exactly. This is what we call a Pythagorean triple. So you may want to go ahead and write that in on your glue tab. Pythagorean triple. Okay, we're going to add a little bit more information about Pythagorean triple underneath the flap. Okay, so if you flip open the flap, let's write underneath it. Pythagorean triple. Okay, obviously Pythagorean triple is a very small occurrence that happens underneath a much bigger formula. What's the bigger formula that Pythagorean triples happen within? The Pythagorean theorem. Okay, so underneath that flap, probably go ahead and write Pythagorean theorem underneath there. Okay, and of course Pythagorean theorem says what? If you have what kind of a shape? A right triangle, then what's going to happen? Okay. A squared plus B squared equals C squared. What's this format called where it says if one thing, then something else? Not converse, but conditional. Conditional format. If, and then you have a hypothesis, then you have a conclusion. Okay, and then you have things like converse, inverse, and contrapositive that can mess around with all that stuff. Okay, now about the Pythagorean theorem. Here we have the triples. Okay, what specifically makes a right triangle be part of the Pythagorean triples like this one was? You get all whole numbers. Okay, all whole numbers. 3, 4, 5 is a perfect example. This is the most basic Pythagorean triple that we run into. Anybody remember the next one up from there? Okay, 5, 12, 13 is the next Pythagorean triple that we run into. There's tons and tons and tons of them, but the values get much larger very quickly from there. The only other thing I want you to put down there or for you to consider on this is that the multiples of these also apply. Okay, don't really know a good way to write it or to say it. Okay, to put multiples also. And what that means is if you took a 3, 4, 5, multiplied all those sides by 2, ended up with a 6, 8, 10, okay, you're going to get the exact same triangle again. So it's the idea that you can reduce by a scale factor, okay, down. So 3, 4, 5, 6, 8, 10, 9, 12, 15. Those are all multiples of the 3, 4, 5. Okay, so same thing. You could double all these values on the 5, 12, 13, get a 10, 24, 26. That's going to work also. Okay, so a lot of times if you run into a Pythagorean triple question, it's either going to be a 3, 4, 5, a 5, 12, 13, maybe a 7, 24, 25, or it'll be a multiple of a 3, 4, 5, or a multiple of a 5, 12, 13. Okay, they usually don't let the numbers get to be too big on there. Okay, but there you go. That's your information on Pythagorean triples. Next, we're going to scooch over. We've got a couple of things glued in next to them, a couple of triangular figures. Okay, on one instance, we have a triangle glued in like that, and we also have a triangle glued in like that. Okay. Now, these triangles that we have glued in, the one on the upper left-hand side, that was an equilateral triangle. We folded it over and we glued it in. Okay. Now, we also talked about what kind of a triangle that would make this. Anybody remember what kind of triangle this is? It's a right triangle, yes. Okay, but more specifically, okay, it's a 30, 60, 90 special right triangle. And it's 30, 60, 90 because we started off with that overall triangle. Remember when we had it, the entire shape? Okay, we folded it over since it was regular and a regular triangle to begin with. It was 60, 60, 60 in all the corners. So we do have a 60 in the corner, and this 30 down at the bottom was split in half. So this is a 30, 60, 90 special right triangle. Okay, that's its name. And if you happen to run into a 30, 60, 90 special right triangle, okay, it has formulas that are on the formula chart. Okay, and we're going to get to that here in just one moment. Okay, on the other guy, what kind of a triangle is this one? Okay, yep, 45, 45, 90. Because if you remember before we folded it, okay, it was a regular quadrilateral. Okay, so we had 90s in all the corners. Those 90s were split in half, and we ended up with a 45, 45, 90 special right triangle. Okay, and if you happen to run into a 45, 45, 90 special right triangle on your test, okay, remember that you do have formulas that go with it on your formula chart. Okay. Now let's unfold these triangles and let's look at what those formulas are going to do for our different side lengths that we have. Okay. Inside of the 30, 60, 90, okay, we had 60 degrees in each of the corners. When we made the fold, we caused ourselves to have some right angles in there, and the 60 that was down here was split nicely into 30s. Okay. Now, 30, 60, 90s have particular names to their different sides. The names are hypotenuse and long leg and short leg. Okay. How do we position these guys inside of the triangle? Where would you find hypotenuse at? Always across from the right angle. Okay, so that would be a hypotenuse because it's across from the right angle. And it'd be the same thing over here if you wanted to do on both. So what you might want to do is you might want to, inside of your little triangle in there, you might want to label that guy's the hypotenuse. And if you can't remember why it's the hypotenuse, then make yourself a little note. Hypotenuse, always across from the right angle. Okay, how about the short leg? How do we find the short leg? Okay, in this case, it's going to be up on top. Why is it up on top? Because it's always across from the 30-degree angle. The short leg and the small angle are always going to be across from each other. So if you got the 30 there, that's going to cause your short leg to be across from it there. Same thing on this side. Okay. And the last thing would be for the long leg. The long leg and the 60 are always going to be across from each other. Okay. So the long legs are going to be these guys that are there. Okay, so aside from all my dotted lines that I just put all over the place that really cluttered up the diagram, that's the positioning of the three different side links that you have for your 30, 60, 90. Okay, now based on the formulas, okay, on the formula chart, okay, what you're going to see is that everything is based upon the size of the short leg. Okay, the short leg kind of controls everything else. So typically what we say, and add this to your triangle, is your short leg is X. We don't know. Okay, either it will be provided for us or it will be one of the things that we are searching for. Now, quite clearly, if it is X across the short leg on the left and X across the short leg on the right, then how long is it all the way across both those short legs? It's two X's, right? X and X. Well, what do you think's going on with the hypotenuses? Those are both two X's. Okay, that stands to reason, right? Because we said it was a regular triangle to start with. Okay, all we did was fold it in half. Okay, so you got 2x across all of your sides. The long leg is the one that's a little bit of the issue. Okay, and the rule straight off the formula chart says the long leg will equal whatever the short leg is times the square root of 3. Okay, so add that into your triangle as well. That long leg is x root 3. Okay. And what a lot of people choose to do, very easy way of keeping it all organized, is to build yourself a little chart. Short leg, long leg, hypotenuse. The rules straight off of the chart say short leg is x, long leg is x root 3, and hypotenuse is 2x. Then these bottom little squares right here, you can simply write in whatever you do know or whatever you don't know, okay, and use the boxes above them. Kind of plug it all in. A little bitty jigsaw puzzle there, okay? So anyway, there is that. The other guy we need to take a look at the measurements of is the 45, 45, 90 that you have down there. Okay, I didn't draw it really very well. My malfunctioning board is not helping. Okay, we started off with a regular quadrilateral. We folded it up. Okay, so we ended up with a 90-degree angle down there. We ended up with 45 degrees there. We ended up with 45 degrees there. Tell me what you know about the two legs of this triangle that you have there. Okay, you know about these two guys. They're congruent. Why are they congruent? Yeah, it's a regular square, okay, and probably a little bit more specifically, what happens if you have two angles in a triangle that are congruent? What does it mean to the sides that are across from them? It means they must be congruent also because of that connection. So one thing you might want to go ahead and mark in your picture is go ahead and mark that the legs of your triangle are going to have to be congruent in a 45, 45, 90. Okay. From there, all right, just like in a 30, 60, 90, the short leg was kind of in control of all the measurements. In a 45, 45, 90, the legs are in control of all the measurements. Okay, so the legs get the X in this case, and since they're congruent, it's X in both cases. And the hypotenuse, which is still across from the right angle, the rule is the hypotenuse is whatever the leg is times the square root of 2. So add that into your triangle as well. And again, if you like the little chart idea, okay, well, you've got a leg and a hypotenuse. The legs are going to be congruent. The hypotenuse is whatever the leg is times the square root of 2. Okay, and then whatever the problem is doing, you can just take the values that you do know, okay, plug them in there, and just follow along with what the chart's written. And again, that chart's basically just written by reading the formula chart. Okay. Now also keep in mind, if you do not particularly like the special right triangles, that's fine. You don't have to. Because if you have enough information to decide that you actually have a special right triangle, then you have enough information to use your trig function. So if you like SOHCAHTOA better than you like the special right triangles, that's fine. Okay, if you have enough information to decide it's 30, 60, 90 or decide it's 45, 45, 90, then you've also got enough information to work the sine function or cosine function or trig function, and some people are more comfortable with that. Just something to keep in mind. Okay, so that's going to be all the information that we're going to add in on reporting category 2. So turn the page into reporting category number 3. All right, now at the bottom of the first page, we have 8 different terms that right now we do not have a definition or a diagram for. We need to add that in. Okay, so now I was not specific about how you put those in there, so you all have them at different in different orders. So just follow along, and we'll see if we can get some diagram or some definitions along with them. Okay, so let's have a look. The first term that I happen to have is a perpendicular bisector. Okay, doesn't matter what order you have it in. Okay, just find your tab that says perpendicular bisector. Perpendicular bisector is a term that is typically used in triangles. Okay, so what you probably want to do is add yourself a triangle. And I don't know if you have separate colors that you can use to help differentiate between stuff, but a perpendicular bisector does exactly what it sounds like it does. It is going to be perpendicular to something, and it is going to bisect something. And these type of structures, okay, when we put them into triangles, what they are doing is they are connecting one vertex to the side that is across from them. And in this case, since it's perpendicular, it is connecting so that it is perpendicular. If I could get my board to draw a right angle. Okay, we're going to get a right angle in there. And since it says bisector, that means we're also getting these guys. Okay, so this structure right there, that is the perpendicular bisector. Okay, so there's one of your little diagrams. We have another term that says median of a trapezoid. Okay, this is actually fairly easily confused with one of the other terms. In fact, they are often used interchangeably. Okay, but a trapezoid, as we should well know, its defining characteristic is it has exactly one set of opposite sides parallel. Okay, so there is a trapezoid. Now, in order to be a median of a trapezoid, what it is going to do is basically going to be a line segment that is positioned in here across the trapezoid, running parallel to the two bases that we have. Okay? And a median of a trapezoid, its main little property is that whatever the length of one of your bases is, and whatever the length is of your other base, if you take the average of them, then you get the length of the median. So that guy right there, that is your median. That is what the thing actually is. Median of a trapezoid, it is that guy right there. The next term I am looking at is apothem. Okay, so apothem. Apothem typically only shows up in what we have come to know as regular polygons. Okay, regular polygons. It could be a regular triangle, it could be a square, it could be a pentagon, hexagon, whatever. Okay, but an apothem, basically the definition for it is the shortest distance from the center point over to the side. And that will happen in such a way that that is perpendicular. Okay, that is the shortest distance between the center point to the side. So that's your structure right there. That's an apothem. The next term I see is diagonal. This should be one of the easier terms that we have out of these 8. And all a diagonal does is it connects non-consecutive vertices. Okay, so if you pick a point and go to any point that's not right next to this one, connect it, that's the diagonal. Obviously, we wouldn't want to connect a point that's right next to the first point that we picked because that would simply be a side of the polygon. Okay, so you go through the internal space, that's a diagonal. Okay. Next term I've got is altitude. Okay. Altitude typically also exists in a triangle. Okay. And the word altitude, and you may want to add this to your card, altitude is also well known as height. Okay, any of your formulas that you have that refer to height, you are hunting for an altitude. And as we should know pretty well by now, height happens when you are perpendicular. Okay, so if we connect a vertex to the side that's across from it, we are going to want to be perpendicular to that side. That's an altitude. Next term I've got is mid-segment. Now, mid-segment is often confused with a median of a trapezoid that we were talking about here a moment ago. As a matter of fact, if you were to look at a mid-segment or a mid-segment of a trapezoid, you would end up with exactly the same thing that we ended up with a moment ago. Now, there's only one thing that really goes differently with a mid-segment. Okay, and that is this. Mid-segment basically means we're going to find the midpoint of one side and the midpoint of another side, and we're going to connect the midpoints. So if I come over here on the left leg of this trapezoid and find its midpoint, and then come over here to the right leg of this trapezoid and find its midpoint, and then connect it with a line segment, then this is what we call a mid-segment. Okay. What separates this from what we saw a few minutes ago on a median of a trapezoid? Absolutely nothing. This works exactly the same way when we're talking about a trapezoid. The only difference is that a mid-segment can exist in any shape. So it is just as likely that if it comes down to a mid-segment problem, you may see the mid-segment of a triangle just as much as you may see the mid-segment of a trapezoid. And again, if we come up one side of our triangle, find its midpoint, come up another side of our triangle, find its midpoint, connect the two, that is a mid-segment. And something else I probably should have mentioned is the mid-segments end up being parallel when they get put in the shapes this way. Okay, so if in the event they do talk about a mid-segment, that is what they're talking about. The next to last one that I have is probably one that everybody should be familiar with. It is angle bisector. Once again, something that happens in triangles fairly often. Once again, we're going to connect one vertex to a side that's across from it, but this time, instead of really being concerned with how it intersects the opposite side of the triangle, we are only concerned with that angle at that vertex getting cut exactly in half. So I put the little angle congruency marks in there to indicate that those two angles are congruent. Okay. The last one that I have is the median of a triangle. And once again, like very many of the terms we've come across, we're coming from a vertex of the triangle to a side that's across from it. In order to be a median, it must bisect the opposite side. Okay, so there are some basic diagrams for your 8 terms that are in reporting category number 3. Okay. On the next page over, we've got a very curious foldable. I'm not sure how much I really like this one, but it's the one that's got hands-on formulas and using formulas across the middle of it. And you've got 4 flaps going upward and 4 flaps going downward. I'm going to give you some information to add on those 4 flaps. And we'll just go with it from there. Okay, so there's a crude drawing of your 4 flaps. Okay, what I want is at the top of these flaps, okay, I'm going to write in some words. Okay, these 2 flaps on the very left-hand side, these are going to be about length. Okay, length. And you may want to put yourself maybe a little drawing, something like that. I don't know. The next little stack of flaps is going to be about slope. Okay, and of course, slope is typically rise over run. Okay, next little group is midpoint. And of course, midpoint would be something more along the lines of that, making sure that a center point is equidistant from both of its end points. And the last flap we're going to add is our linear equation, y equals mx plus b. Okay, now this remaining information we're going to put on the inside of the flaps. Okay, the way this foldable is organized, it suggests that there ought to be some information about hands-on methods and then some information about formulas. There's more information about formulas than there is hands-on. As a matter of fact, I do not know of a very good, dependable hands-on method for finding the length of 2 points. Sure, if you're in a graph and they're straight across side by side, you can count the number of steps. Sure, if they're stacked on top of each other, you can count straight down the number of steps. What happens if they're diagonal in a graph? I know I've bumped into some teachers that have told y'all in the past that, hey, even if it's diagonal, you just count the number of grid lines that it runs across, whether they're going sideways or vertical or whatever. And you know what? That may accidentally work sometimes, but it very much does not work all the time. So I would abandon that if you've had a teacher tell you that. So as a matter of fact, on the hands-on version, inside of that flap, okay, on mine, I've got not applicable. Okay, that there is not a hands-on or a simple way of coming up with the length of a line, especially if it's diagonal. Now, inside of the hands-on for slope, okay, very easy. If you got a graph, you can count it. Rise over run. How much does the y change compared to how much does the x change? Very easy. Midpoint. Did you know that you can actually find the midpoint of a line also using slope? Okay, if you didn't know that, here, learn it now. Still can find rise over run, but whatever that is, that value, that fraction, divide it by 2. Instead of getting you all the way from one point to the other point, that'll get you halfway from one point to the other point. Tell you exactly where the midpoint's at. Okay, and as far as the equation of the line is concerned, if we are lucky, we can go rise over run to get our slope value. And if we're also lucky, we'll be able to get our y-intercept value right out of a graph. Okay, now that's if we're lucky. We'll talk about what happens if we're not lucky here in just a second. Now, underneath the bottom 4 flaps, okay, for the using formulas methods, the length of a line in a graph, okay, whether it's sideways or vertical or diagonal, Pythagorean theorem can get you there. Build a triangle. Figure out which side of your triangle is missing, plug it into Pythagorean theorem, run it through a squared plus b squared equals c squared. We ought to be very comfortable with that by now. Okay, so there's that. Okay, there's another one for finding the length of a line, and that is your distance formula. Okay, and that's that big nasty one that's on the formula chart. Some people don't mind it, some people do. The difference of the x's squared plus the difference of the y's squared, and it's all underneath a square root. And whether you realize it or not, or whether you can see it or not, the distance formula and Pythagorean theorem, very much the exact same formula. They look very, very different from each other, but they actually do the exact same math. Okay, so anyway, there's those. For slope, everybody knows the slope formula. If you don't, it's on the formula chart. Y2 minus Y1 over X2 minus X1, straight off of the chart. Also, midpoint formula, straight off of the chart. The sum of the x's divided by 2, comma, the sum of the y's divided by 2. And back to the equation of the line, we said if you're lucky, you can get your rise over run right out of your graph. You can get your y-intercept right out of your graph. What happens if you cannot? Okay, well, you've got an equation. Y equals mx plus b. As far as m, where can you get m from? Well, you can get m from back here. Okay, we can calculate it if we have to. And then what happens if you cannot get your y-intercept out of your graph? That's fine. Take a point out of your graph and plug it in. Okay, using all that information, you ought to be able to plug in for y, you ought to be able to plug in for m, you ought to be able to plug in for x. That would leave your y-intercept as your only unknown value, and you can solve for the y-intercept from there. Okay, so there are the formula methods for coming up with that information. Okay, that's the end of reporting category number 3 of the stuff that we need to add in there. So flip over to reporting category number 4. Okay. Down at the bottom of the left-hand page, you have a colored foldable, and it's got a pocket inside of it. Okay, when you open up your, actually on the cover of your foldable, what I want you to write down there is surface area or volume. And it's a question. The cards that you're cutting out on surface area and volume are going to be for this foldable. And when you open this foldable up, okay, what you've got is something along the lines of that, a fold right through the middle of it. This bottom rectangle is a pocket. Okay. And basically what I want you to do is on one side of it, okay, write surface area or volume. And as you're working with those cards and you're looking at them, okay, you can sort them and you can put them into the different pockets. Okay, that's what those cards are for. And hopefully tomorrow we'll be able to come back and we'll talk about a little bit more about the cards and how you use them and stuff like that. Okay. The other thing I want to look at real quick in reporting category 4 is the circle that you've got glued in there. It should look like a semicircle the way you've got it glued. Okay. What I would like you to do is in the top quadrant for this circle, what we're going to do is we are going to draw in something along the lines of this. Basically making a little problem inside of there. And we are looking for this information. Okay. Well, while you're scribbling that down, what is that actually called? This guy that's right here, this highlighted piece, what's that called? It's got a vocabulary term. It's an arc, exactly. Okay, so you may want to write that in, arc, or perhaps, depending on how tricky the test writers want to go, they may call it arc length. Okay, but either way, it's an arc. Now, when you open up your foldable, basically you got this. Okay, and what I want you to do is I want you to write in there how we actually go about solving for that arc length. Okay, and there is a formula, and the formula basically says, okay, it's an arc, which is a portion of the circumference. That's 2 pi r. Okay, how do we know what portion of the circumference is actually going to be? Well, we apply how much of the circle it covers. Okay, theta out of 360 degrees, where theta is the angle measurement down inside of that side of that arc. Okay, and there you go. We're going to do the same thing on the outside of the circle down here. $30, only this time maybe it's looking for all of this space that's inside of here. Okay, what's that called when it's looking for the area of a portion of a circle? Remember that one? Kind of vocabulary term also? No? So it's called a sector. Portion of the area of a circle is called a sector. It has a formula that goes with it also. Okay, it's the portion of a circle. A circle's area is found by pi r squared. Okay, but it's only a portion of the circle. So once again, theta out of 360 times pi r squared. That's how we find its area. Okay. All right, one other thing that's on that page, and maybe a little difficult because the way I copied everything, it didn't work out. The flap at the top of the second page, the one that lifts up and then folds open, it's got regular polygons inside of it. That is area of regular polygons. You might want to go ahead and write on the cover, write area of regular polygons on that little foldable so that you actually know what is in there. Okay. Okay, the last two things that we need to fill in as far as written information, they are in reporting category number 5, and they are the two colored foldables that we put in down at the bottom of the first page. Now the one at the very bottom, it is a rectangle, okay, horizontal rectangle, and it unfolds into 4 quadrants. On the cover of that, what we're going to write in is change in dimensions, which is something we have spent quite a bit of time talking about here in the last couple of units. Now, as you unfold that foldable, you'll end up with something closer to that. This bottom left-hand rectangle down here, that's the one that's glued in if you glued it in the way that I said. Okay, but when you open it up, what I want you to do is I want you to write, okay, in the left-hand corner, this is the first dimension, second dimension, third dimension, and not fourth dimension. That wouldn't make any sense. Okay, next one is proportions. Okay, what we're going to do is we're going to write in the different measurements that we have that are in these different dimensions. Okay, first dimension, scale factor. Scale factor is a first dimensional measurement that we deal with. And it's first dimensional because the scale factor directly refers to the relationship amongst the side lengths. Okay, so scale factor and side lengths are both first dimensional measurements. And since the side lengths, when they're added together, become perimeter, then perimeter is also a first dimensional measurement. Okay. Second dimensional measurement, all we have in the second dimension is area. That includes two-dimensional area of a polygon and also surface area on a three-dimensional polygon. On the third dimension, the only measurement that we have is volume. Okay, and then the information about the proportions. Okay, and what I want you to write in here, I don't have much space on my board here, but what you want to write in there is, are the sides, or the sides of the proportions in the same dimension? Are your two sides of your proportions in the same dimension? They need to be. Okay, so if you set up a proportion and you look at the ratio on the left and look at the ratio on the right, they need to be in the same dimension. If they are, if your answer is yes, then solve it. If your answer is no, then you need to adjust, which usually involves squaring or maybe cubing one of the sides, depending on what dimension you've got going on, and then solve. Okay, so that's the information for that guy. Now the other foldable, okay, when you're looking at it, it is more vertically oriented. Okay, and what we're going to write in here is solving by trig. Okay, this is sine, cosine, and tangent. Now, depending on which direction you open this thing up, you will either end up with 3 panels or 4 panels. And what I want you to do is I want you to open it up the direction that it has 3 panels. Okay, so when you either open it up and pull it left or open it up and pull it right, one way is going to have 3 panels, one way is going to have 4 panels. Now, the way that has 3 panels, you're going to see the information that you just wrote on there, solving by trig. Okay, that'll be one of the panels. Okay, on the second panel inside of there, what I want you to do is I want you to construct yourself a triangle. Okay, we're going to need an acute angle, theta. Okay. Across from our right angle is our hypotenuse. Always across from the right angle is always the hypotenuse. Across from the acute angle, that is our opposite side. Hypotenuse. Across from the theta is opposite, which leaves next to theta is adjacent. It's important to know where hypotenuse and opposite and adjacent are positioned because that is what SOHCAHTOA is based on. And that's going to get the third panel. Okay. Obviously, SOHCAHTOA, those are 3 groups of 3 letters. Sine equals opposite over hypotenuse. That's how you read the top line. Second line, cosine equals adjacent over hypotenuse. Okay, last line, tangent equals opposite over adjacent. Those are the 3 panels for that direction of your opening. Okay, now fold it the opposite direction, which should give you 4 panels. Okay, and this is going to be a step-by-step for how to solve your trig. Okay, step number one, anytime you're working with your calculator on trigonometry, is check your mode. Okay, push the mode button on the calculator. It had better be in degree mode. Okay, if it's not in degree mode, then set it to degree mode. If it's not in the correct mode, anytime you push sine, cosine, or tangent, you are probably going to end up with an incorrect incorrect answer. Second step, label your triangle. Okay, that's just like the second panel from above. Okay, let's label where is the hypotenuse, where is the opposite, where is the adjacent, and of course opposite and adjacent are going to change according to which angle we are calling theta. The third step will be to select the right ratio. Okay, based upon the information that you have in the problem, either you're going to have opposite and hypotenuse, and that would be sine, or you're going to have adjacent and hypotenuse, and that would be cosine, or opposite and adjacent would mean tangent. Okay, from there, on 4, you're going to set it up, meaning you're going to plug into the ratio that you picked. You are going to solve it, which will bring you an answer to your problem. Okay, and keep in mind, use the inverse trig buttons, okay, or the inverse trig functions, which are the ones that say things like sine to the -1, cosine to the -1, tangent to the -1, and you use those anytime you're actually trying to solve for theta. Okay, so you have sine theta, tangent theta, cosine theta. The only way to separate the trig function away from its an unknown angle measurement is to use the opposite of sine, or the opposite of cosine, or the opposite of tangent, which are arc sine, arc cosine, and arc tangent, in order to do that. And if you have trouble with that, drop by and see me, and I'll help you with that. Okay, that should basically conclude the written in information for the notebook. We need to get the rest of those cards all cut out. You need to be on top of your vocabulary packet. The days are getting short. We are now 4 days away from the geometry end of course. We have simply run out of time and are unable to do everything that needs to be done just working on it in class. So please stay up with it. It'll not only help you with your getting ready for end of course exam, but for those of you that are tax as well, this is also a review for getting ready for a semester exam. So keep on top of it.